Great. Thanks for the introduction again, Michael, and thanks everyone for coming. The topic I wanted to talk about today is design tools for digital fabrication. And as many of you may know, digital fabrication has become probably one of the most kind of active or hot topics in computer graphics, which is kind of mainly the community that I come from, but as well as HCI. So, why have I, and to be fair, others as well, kind of jumped on this fabrication bandwagon, so to speak? Well, one reason that you've probably heard before is the rise of digital fabrication technology. So things like 3D printers, laser cutters, CNC machines. These things are becoming more affordable and more accessible than ever before. And that's making it possible to create a variety of different things in a variety of different materials easier than ever before as well. So I think that seems to present or offer an opportunity to think about and develop some new user interfaces and interaction techniques, as well as computational tools to help people create this variety of different types of physical artifacts. Okay, so that's kind of the status. And I just tried to look back over some of my favorite fabrication papers over the last several years, and I found that more or less they kind of fell into three broad categories. So there's been a lot of projects that focus on building design tools that empower new users. So these are people who may not have the expertise to use traditional CAD or CAM tools to create things, to design for fabrication. And so there have been systems, we've seen systems for helping people build kind of complex furniture, as well as figurines that can balance and stand on their own. Another category of work is just exploring the new types of things that we can create with rapid prototyping technologies. And some of you may have seen the work by Wil Li et al. On printed optics, where they embed these 3D printed light pipes inside of objects to create or enable these kind of dynamic and tangible display surfaces. Also, Valkyrie Savage and her colleagues at Berkeley have been working on a few different techniques for creating 3D printed tangible input components, like game controllers or mixing boards, let's say, that are kind of functional. They're interactive, they work with computers, but they don't require you to actually wire up a bunch of electronics in there. They use things like computer vision and audio signal processing to detect and interpret these interaction events. And finally, there's this kind of interesting category of new work that's been coming out that really looks to understand understand design workflows that make use of digital fabrication and try to improve or optimize those workflows. So in particular, Stephanie Mueller and her colleagues at HPI have done a lot of really cool recent work that tries to just figure out some of the inefficiencies in existing design workflows that involve 3D printing and just minimize those or kind of work on those inefficiencies to try to make design iteration much quicker. So these are three kind of broad categories of work. There are probably other ones. Most of what I'll talk about today falls into this first category. But I'm interested in these other categories as well, and I'm hoping that at some point I get a chance to work on some projects in those domains. Okay, so if we're talking about trying to empower new users to design for fabrication, who might these users be? Well, I think on one hand, some of them could very well be industrial designers. So these are people who are already kind of embedded, already participating in the process of creating physical things. But in some cases, at least, not all of these designers may have the kind of engineering or CAD expertise to create working physical models on their own. So maybe they have to work with mechanical engineers or a print shop. And so the opportunity here is, I think, to kind of reduce that kind of friction in the design workflow and hopefully make it easier for designers to create and fabricate some of these objects themselves and then hopefully thereby iterate more quickly. There's also a large community of makers out there who are interested in creating a wide variety of different types of objects. And again, these people may not have the expertise to create physical objects completely on their own. And then finally, there's, I think, what I would call just a long tail of other people. Maybe let's just call them consumers. This is kind of a really common term that's bandied about in Adobe, probably other companies as well. It's like, oh, this is a block of people. They're consumers. It means they're willing to spend money on something. But for consumers, I think, for these consumers, the interest may be more in terms of just kind of personalizing some of the objects that they buy or they have in their possession. So maybe putting photographs on their iPhone cases, or maybe designing exactly which combinations of colors and materials your shoe should be composed of. So this is kind of they're a very different, I think, segment than designers and makers, but they're still kind of interested in participating in this kind of design process at some level. So in addition to having all these different types of potential users, obviously there's lots of different domains of physical objects that we might consider when we're thinking about building design tools. So clothing and furniture and jewelry, maybe even you want to design your own modern prefab house. So each of these domains probably consists of produces some of its own challenges with respect to developing effective design tools. In the last part of my talk, I will discuss what I think are some opportunities that kind of may span some of the many of these different categories. But for most of today, I'll be talking about some work that falls under the category of kind of mechanism design. And in particular, I'll talk about two projects. One that focuses more on kind of enabling hobbyists to create working mechanical objects, and the other one that focuses more on designers. Okay, so why are mechanical objects kind of an interesting domain to look at? Well, first of all, they're extremely common, and you may be thinking about things like cars and construction equipment and other kind of industrial machinery. These are clearly all examples of mechanical objects, but kind of at a smaller, more kind of day-to-day scale, there are things like toys, like wind-up toys, for instance, and also just lots of household objects consist of mechanical components. So there are lots of these mechanical objects out there, and the other thing is that they tend to be pretty difficult to design. So there's lots of parameters that are associated with these mechanical objects, and those parameters are coupled and constrained in interesting and challenging ways. So there may be kind of like a pretty big parameter space of designs to consider, but only a relatively small set is actually valid or it does what you want it to do. And so while people with a mechanical engineering background or an industrial design background may be capable of kind of finding this right set of parameters, it can be a pretty daunting task for for other designers or for hobbyists, and certainly for novices. So the question is, how can we kind of help these different types of users create some of these mechanical objects? Okay, so before I get into the specifics of these two projects that I'll talk about in this space, I wanted to take a brief diversion. Since Michael mentioned at the beginning, I want to talk a little bit about some other work that I've done previously, just to give some context for how I got interested in mechanism design in the first place. So a problem that I've been interested in for a long time is how can we help people visualize and understand the internal structure of complex 3D objects that contain lots of different parts. So mute that. For instance, anatomical models or CAD models, these are examples of the types of data sets that I'm interested in. And during my PhD, I worked on a bunch of interactive visualization techniques that are inspired by traditional technical illustration, so cutaways and exploded views, and tries to kind of automate these techniques as much as possible so that we can have a kind of this interactive viewing experience. And so what you're seeing here is just some videos of these two systems where, for instance, the user can just search for the parts that they care about, and the system will automatically generate either a cutaway or exploded view that just shows you those parts. These systems also support other types of interaction, like hovering over parts and also clicking on parts to kind of explore these types of objects a little bit more interactively. Okay, so these types of systems, one thing that they help people do is understand the kind of spatial configurations of parts that exist inside of these objects. But one really common comment that we got from people who saw this work was, okay, that's great, but I really also want to know how these things work. Like, how does this engine work? It's got lots of moving parts in it. I guess people did not ask so much how the arm works. So for anatomical data sets, it was a little bit different. But especially for these CAD data sets, they were like, I really want to know not just where all these parts are inside of these objects, but how they work. And so that kind of led us to some follow-on work where we looked exactly at that question. And so in this work, we took as input a 3D model. So this is just geometry, no kind of other annotations. And then given a specification of some kind of driving force at some part, what we tried to do is to create visualizations that show how these things, or tried to convey how these things actually functioned. And some of a lot of our visualization techniques were inspired by the How Things Work books that Michael mentioned earlier. So for instance, these types of kind of motion arrows that annotate where the mechanical interactions occur and also how the parts move. But we were also inspired by a lot of cognitive psychology research that really emphasized the importance of the so-called kind of causal chain of mechanical interactions in understanding how these things actually work. And so here's a different visualization that just highlights each step in this causal chain, how the force kind of gets propagated throughout this assembly in particular. And then, of course, since we have this information about how since we know something about how this assembly actually works, we can also create animations like the one you see here that are kind of in an illustrative style, but show the assembly in motion. So I don't want to go into too much detail exactly on how this technique actually works, but I did want to describe the high-level approach because I think it's relevant to some of the subsequent parts of the talk. So the high-level approach was we took an input model on the left. Again, this is just geometry, and then we did some geometric analysis in order to figure out how this thing actually works. And in particular, we construct a graph. We call it an interaction graph, but there are other names for it in the literature as well, where each of the nodes represents an individual part, and the edges represent these mechanical interactions between parts. So this graph really kind of defines or encodes the functionality, the mechanical functionality of the object. And based on this graph, we can derive all the different visualizations that I just showed you. So that was kind of the overall approach. Okay, so what does this have to do with mechanism design? So after working on this project, it kind of occurred to us that one thing we could try to do is kind of turn this approach on its head and maybe use that as an approach to helping people design physical objects or working mechanical objects. So in particular, let's say, as opposed to taking an input model and then trying to figure out how it functions, maybe we can ask people to specify some desired kind of goal functionality, and then use that as part of our system, as part of a design system, to help people create working mechanical and physical designs. So that's kind of the really high-level approach that the next couple of projects I'll talk about take. And just to be really clear here, this is certainly not really a new idea. I mean, I'm not an expert in mechanical engineering, but I know there's a ton of work on inverse design. This is basically an inverse design approach. On inverse design that focuses on helping engineers create things like optimize the design of turbines and airfoils and gear trains that accomplish specific design goals. Maybe Bill can say more about this at some point, but there's a lot of work out there that does that. My impression is that a lot of this existing work does still kind of focus on how can we help a mechanical engineer solve a specific challenging design problem, and as a result, a lot of the kind of input functionality in its previous work, I think, tends to be somewhat low level. So here's a desired kind of gear ratio for two particular gears in a gear train. Now, how can we help the engineer create the corresponding mechanism? So what we've been interested in exploring are some methods and some user interfaces as well that kind of allow for users to specify some higher level functionality, and hopefully in doing so, kind of open up some applications that are relevant to people like the hobbyists and the designers, and maybe even the novices that I talked about earlier. Okay, so that's kind of the basic approach, and let's see. Did we just jump right in? Yeah, so let's just jump right in, and I'll talk about these two projects that I've worked on recently. So the first one is really focusing on hobbyists as a target audience, and the goal is to help them create mechanical automata. And so these are things like what you see here. So on the left, these are actually example mechanical toys from the 19th century, and so these automata tend to look more or less like humans and perform some kind of repetitive motions. And they're all mechanically driven. So typically there's this one kind of input crank, and you turn it, and the thing kind of does, performs these repeated motions. But mechanical automata are not just things of the past. They exist in our current lives as well. And one common example are just wind-up toys. So there's lots of kind of toys out there that are still largely mechanical. But even like in things like stage production and I think theme parks, they still use things that we could more or less call mechanical automata to create these kind of like moving characters, moving physical characters. And although I'm not an expert in visual effects, I believe that up until recently, visual effects still also used in some cases, mechanical automata to create certain types of creatures and those kinds of things. So, these are some really interesting types of mechanisms, but obviously, or maybe not obviously, they're hard to design. I mean, you have to worry about a whole bunch of interacting mechanical components and have them kind of achieve these specific target motions. So the goal in this project was just to try to make it easier for users who are not mechanical engineers, who are not expert toy designers, to create these kinds of outputs. In particular, the approach, the kind of design pipeline that we took was to have people specify as input some kind of motion. And this is in the form of an animation. In this case, it's motion capture animation. So let's say we have this input motion. Then what the system helps the user do in a largely automated way is to turn that into a mechanically realizable form of that motion that that also has solved for all the different mechanical parameters of the parts that will create that motion. And again, in this case, we are trying to work with this kind of single input crank constraint. So this thing should be able to be driven by a single input crank. Okay, and then based on that design, we can now actually fabricate a working version of the automaton by, in this case, laser cutting the different parts and then putting them together. Okay, so just a little bit more detail on how this actually works. I won't go into a lot of detail. One of the main insights, one of the main aspects of the technique was, as I mentioned before, we're trying to allow users to provide some really high-level functionality here, and that makes things challenging. Like there's lots of different ways of achieving any of these input motions, right? And so that's a pretty huge parameter space of different configurations that we could consider. How do we kind of make that problem a little bit more tractable? So the way that we did it in this case, the way we had of simplifying the problem was to come up with a single fixed, what we call oscillation module, that has this fixed design, has certain sets of gears, and in this case, a 4-bar linkage that's connected to the gears to kind of turn rotational motion into oscillating motion. And then we attach these oscillation modules to each joint in the model. So now we have basically the same repeated design. It's just a modular design that's repeated across all the different joints, which really reduces the space of different solutions we have to search over. So it's not quite as simple as this. Actually, what we have this kind of a 4-bar linkage. We also connect that linkage to the next limb inside of each of the kind of kinematic chains of the body. So you see this black limb that's kind of moving back and forth. And then finally, in order to be able to propagate the motion from one joint to the next, so let's say the shoulder to the elbow, then we attach this kind of pulley mechanism that then kind of allows the initial kind of driving rotation to be transferred to the next joint in the chain. So this is kind of the basic design element of this technique. And with this oscillation module, we basically run an optimization that takes that input motion and then comes up with an approximated motion as well as the design that kind of solves for all the parameters of the module. Now, I should say here, there's definitely a trade-off here. I mean, on the one hand, we've created this oscillation module that makes the parameters, that reduces the parameter space we have to care about. But on the flip side, it also kind of restricts the range of different motions that we can produce, right? And so that is kind of the fundamental trade-off that we decided to make. In spite of that, we were able to use this approach to kind of reproduce an interesting range of different motions. So let me just show you a few results here. So on the left is, in each case, is the input motion. The middle is kind of the mechanical motion. So we're not showing the mechanisms just yet, but we're just showing the difference between the input motion and the motion that we're more or less able to achieve mechanically with these oscillation modules. So one constraint here is that we're restricting the motion of any individual chain, like the arms or the legs, to be planar, but those can exist in different, so the arms can move in a different plane than the legs. It's just that each arm or each leg has to have a more or less a planar motion. So these are a bunch of different motions that we grabbed from a motion capture data set. And in a minute here, you'll see a couple of the fabricated results. Oh yeah, we can also use a Connect or something to then demonstrate the desired input motion, and then produce a design that reproduces that motion more or less. So on the fabrication side, this is the walking example that you saw earlier. We laser cut all these different parts, including the limbs, and then we were able to fabricate this example. And we're driving here with a motor at the top. It's kind of hidden, I think, but it's being driven from the top. And then there's, in a moment here, the second sequence, the dancing sequence, which has two different planes of motion. The arms kind of move this way, and the legs move in another plane. And so that's this example here. Okay, so I already talked about some of the limitations of this work. They mainly have to do with our use of this fixed oscillation module. As I said, right now the motion of each individual limb has to be in a single plane, which is fine for some motions, but let's say for swimming, in the swimming example, it really probably wouldn't work very well. Also, as I mentioned, we are assuming there's a single input crank that can drive any of these individual designs, which is on the one hand good because if you have a wind-up toy, you have basically a single input, and that's great. But on the other hand, it can make for some pretty complicated, like we have to jump through some hoops to actually get all these different chains connected up, all these different kind of moving parts connected up so that they can be driven by a single input crank. So that's definitely some more work I think that needs to be done there in order to make these kind of simpler designs. And then finally, the individual mechanical components we use inside of our oscillation module, they're really simple. They're just gears and 4-bar linkages and pulleys, which again restricts the range of different types of motions that we can produce potentially. So if we consider things like non-circular gears or more complicated linkages, I think that could really expand the range of things we could reproduce. And in fact, some other kind of recent work along these lines does experiment with some of these different types of components. Okay, so the system for authoring automata, that was really focused on hobbyists. And so as a result, we were trying to go for like a fairly automated system. You more or less provide this input motion, and then the system generates a result for you. So that's fine for hobbyists, but what if we want to consider other types of users? For instance, industrial designers who, like they're probably going to want to be creating a wide variety of different types of things, and as a result, a design system for those types of users probably needs to be kind of more flexible and give them more control over the types of things that they can create. So that was kind of the direction we moved in for this other project, where we're really focusing on designers and helping them create prototypes. In particular, we are focusing on what some people call works-like prototypes, and so these are prototypes that are often created, I think, earlier on in the design process to try to explore the kind of the functional characteristics of a particular candidate design. This is especially true for mechanical objects. In many cases, the actual geometry or the appearance of these prototypes doesn't have to be very accurate. The point is not to try to evaluate how the thing looks or the form of the candidate design. It's more about the mechanical functionality and as some designers call it, the mechanical architecture of these objects. There's probably it's pretty kind of well agreed upon and well understood at this point all the various benefits of prototyping, and so in particular creating these works-like prototypes I think can really help designers go through multiple iterations in the design cycle, which can often leads to kind of better design exploration. So the goal here is to try to make it easier for these designers to create these kinds of works-like prototypes and then kind of contribute to this better design exploration as a result. So the main challenge that we kind of identified here in talking to some designers about their process is that going from the concept of some kind of mechanical design to a working prototype of that design is often kind of challenging. I mean, even if it's a relatively simple, even if the prototype is relatively simple geometry, as you see here, there's lots of things to think about, like where to put the joints, what are the joint parameters, what are the dimensions of all the parts, so that everything kind of fits together nicely. So, going from design to these working prototypes involves kind of addressing some of these challenges. And while some designers are are probably capable of doing that. Many others kind of have to rely on working with engineers or other kind of experts, CAD experts, to try to help them do this. And so this is kind of the part of the workflow that we were trying to address and trying to facilitate. Okay, so the specific design pipeline that we adopt is, from a design we expect that the user is going to create a really rough model of the object. So in this case, you don't have to worry so much about exactly how the parts line up, where the joint should go exactly, the various joint parameters. Just kind of create a rough model that's based on your initial design. And then what we allow the user to do is now specify specific functional relationships between different parts of this design, or different parts of this 3D model in this case. So for instance, you might say that one part of the model has to cover another part of the model. Or you might say that one part of the design has to fit inside another part of the design. Another functional relationship we support is support. So one object should be supported by one part should be supported by other parts inside of the design. So by specifying these kind of functional relationships, the user is kind of telling us something about what is the desired functionality of this object that they've kind of roughly modeled. So based on this information, we're able to kind of create or update the initial rough model and turn that into a working design. So now the part dimensions have been updated to match or to satisfy all these functional requirements, and also we've generated joints and joint parameters, joints with the appropriate joint parameters to allow this design to actually work. And then we can send this design to, let's say, a 3D printer or some other rapid prototyping technology, and then get a working prototype in the end. Okay, so I'll just say a little bit more. Again, I'm not going to say a lot about exactly how this works, but basically one of the key contributions here was just figuring out a way of mapping these functional relationships, which are specified at a really high level, like this part of the cabinet has to cover this other part of the cabinet, mapping those onto a set of geometric constraints so that we could then use inside of an optimization to take that rough initial model and turn it into a working model. So let me just show you a little bit of the system in action. So here's this kind of rough initial model. Let's say I want these two doors of this cabinet to actually fit or cover exactly the front of the cabinet. So if I specify that relationship, you can see a bunch of the part dimensions have been updated to make sure that that's the case, and also to avoid collisions. This is kind of an example of a fit inside relationship. This is pretty clear. So I want this drawer to fit just inside of the printer cabinet, so that gets updated. And in this case, I'm saying I want the top of this kind of folding bunk bed thing to kind of be supported by all the parts underneath of it. And this is kind of the update that the system makes. So one advantage of having these functional relationships kind of explicitly encoded in the system is that once we have them, we can also allow the user to kind of explore design variations while maintaining these functional relationships. So here, I say, oh, the doors have to cover the front of the cabinet, and they also, in this case, have to fit inside. So those relationships are known. So now as I change the size of these different components, the entire cabinet updates appropriately. Okay, so now given these designs, I'll just show here a few of the fabricated prototypes that we produced. And you'll notice that these have a few different types of joints and different types of parts. They have hinges and sliding hinges, and just kind of sliding parts. And I guess as this plays, I'll just talk again about a couple of the limitations of this approach. So these examples just demonstrate to some extent the range of different objects that we were able to produce, but we're right now only supporting really simple geometric primitives. I said at the outset that works-like prototypes tend to have pretty simple geometry. That's true, but sometimes just having boxes and cylinders is not quite enough. In particular, one example we talked to one of the designers who we talked to mentioned that often for the works-like prototypes that he creates, he wants to see how an existing object kind of fits inside of some other kind of mechanical housing that he's designing. So let's say like a case for an iPhone, let's say, or something along those lines. So even if the actual geometry of the parts of the prototype don't need to be particularly detailed, having those parts fit with other real objects is kind of a nice feature. And so I think clearly to make this approach more useful, we would want to consider these different types of geometric primitives to use as parts. Also, we right now only support a few different types of functional relationships. There's many other functional relationships that I think could be important. Again, that same designer mentioned snap fitting as one potential relationship, or kind of like screwing things together or something along those lines. So there's clearly more work to be done. This is the bunk that we showed earlier. I think it probably wasn't very clear from the 3D model how this thing was supposed to work or what it's supposed to do, but it's kind of this folding sofa bunk design. Okay, so these are just kind of 2 points in the space, but there has actually been a lot of work recently in the graphics and HCI communities on things related to mechanism design. And so some of this work is very related to things that I showed. Others are kind of less related, like for instance in the bottom right, it's a cool paper from SIGGRAPH last year where they're creating things that spin. So basically you take a 3D model as input and you want to try to make it spin like a top. So that's kind of a functional goal that somebody might have, and so that's what that work focuses on. So these are just 2 points in the space, and there's lots of kind of work going on in this area right now. I do think, though, that there's lots more work that could be done. So I think this is a pretty open space, lots of different domains and different types of functionality that you can imagine trying to support in these kinds of design systems. And I just wanted to show one specific example of it's kind of an inspirational example of something that I saw again at SIGGRAPH last year that made me think about an interesting new direction that I think is worth pursuing. So some of you may have heard of Not Impossible Labs, but they gave the keynote at SIGGRAPH last year. And what they do is they try to go out and use technology to try to solve specific problems for specific people. So in this case, this boy, Daniel, who lives in a village in Sudan, was tragically lost both of his arms in a bombing. And they went and they built him a prosthetic arm that allowed him to eat by himself. So basically, in moving the arm kind of also controlled the hand of the arm, so that he could kind of reach out, grab things, and then bring them up to his mouth. And this is kind of made a big difference in his quality of life. But as you're seeing right now, not only did they build a single solution, they tried to basically educate the rest of the village, and in some sense kind of open source the solution so that other people could actually build similar kinds of prosthetics based on the same design. And I thought that was really, it's a really simple observation. It's a really actually noble kind of goal. But the simple observation was that it took a lot of expertise and effort to actually create this one working design. Now, how can we leverage that as much as possible to help other people kind of take advantage of that? And so I think to me, there seems like at least a couple of different, there's one kind of main opportunity here from kind of a computer graphics or HCI research side, which is that I think if we can think about ways of taking individual working designs and then parameterizing them in ways that make it easier for those designs to be kind of adapted to different situations. So clearly, in the case of the prosthetic, everyone's got a different arm, different shaped arm. There's clearly parameters that have to be kind of customized. That's an interesting problem, I think, and I think it's one that's worth trying to address. So that's kind of that's kind of where I'll leave off the first part of my talk, which is really focusing on mechanical design and some of the opportunities there. Let me go back to this slide from the beginning of my talk. As I started out by saying, there are lots of other kind of interesting domains of physical objects that we can consider trying to build design tools for. And so far, we've been talking about mechanisms and their functionality. But what about these other domains? I think there's some really nice opportunities here. And so what I'll do for the second part of my talk is just kind of talk about more opportunities and a little bit of ongoing work. But this is not work that I've done already. This is just kind of some stuff that I've been thinking about that I think is could be interesting to work on. So let me start with a bit of an observation. We've talked a lot about functionality, and in particular mechanical functionality. But those clearly are not the only design goals that go into making physical objects, the ones that we see in the world around us. And just as a couple of examples, this this sculpture by Rodin is not just a kind of anatomically plausible representation of a reclining figure that happens to balance and sit flat on a surface. Just like these chairs are not just some collection of wood and metal and fiberglass that that a human can sit on. I mean, clearly they have a functional purpose, but that's not the only goal here. For these objects, as well as many others, the artists and designers who are creating them are using a variety of techniques to kind of convey certain emotions or convey certain aspects that are beyond just function. And I think it's interesting for us to maybe think about how we could try to be inspired by and leverage some of these existing techniques that artists and designers have created in order to build better computational tools. So as a computer graphics person, it occurred to me that there's a potential analogy we could draw here to the advent of a field called non-photorealistic rendering, which some of you may have heard about. Basically, in the history of computer graphics, people started out for a long time just trying to create more and more realistic renderings, images of 3D models of things that exist in the world today, trying to emulate reality as much as possible. And so, these are just some examples here. These are all rendered images, and it may be harder to tell for some of them that these are actually rendered images. This resulted in a lot of really important advances in computer graphics. So this is great. But at some point, some researchers began to think about and look at some other forms of depiction. And in particular, they looked a lot at things like illustration and painting, which use very different kinds of rendering styles, depiction styles, in order to represent things in the world and represent scenes. And these different rendering styles kind of inspired this whole field of computer graphics, which is often called non-photorealistic rendering, to develop computational tools and algorithms to try to make use of some of these techniques from illustration and painting as a way of creating computer-generated imagery. And this is, I think, as a field, we're kind of better off for it, right? I mean, clearly there are a lot of really important applications for creating super photorealistic renderings. But these other forms of depiction have a lot of advantages as well, especially in terms of emphasizing certain aspects of a drawing, emphasizing certain aspects of an image or of a scene. And it's basically just expanded the expressive range of computer-generated imagery. So I think that's been a great development. Maybe we can think of a similar thing happening for the creation of 3D objects. So can we be inspired by and leverage some of the techniques that 3D artists and designers use and have been using for a long time in order to create tools and algorithms that produce a wider range of different kinds of 3D objects? Let me try to make this a little bit more concrete by going through some examples of techniques that I think could potentially inform design tools for creating 3D objects. So one really simple one, I'll go back to this example that I showed before, is simply about abstraction. And of course, abstraction is a big element of a lot of 2D artwork as well, illustration and painting. But in 3D, it may not be quite as obvious, but it exists in 3D as well. So for sculptors who create busts of human heads, they often refer to this abstraction called the planes of the head, which is a set of planes that define more or less the kind of key characteristics of a person's head and their face and what they look like. And so in order to create really kind of compelling and recognizable busts of humans, they often kind of end up abstracting away a lot of the details and really focusing on these different planes of the head. For kind of full body anatomy, like as in this example here, abstraction is also happening, clearly. I mean, maybe a little bit hard to see in this slide or in this room, but the face and the hair of this figure are clearly abstracted away a lot. There's not a lot of detail there, whereas kind of the back and other parts of the form have a lot more detail. I found this other version. I mean, this is not another version of that sculpture, just a different version, a different sculpture that seemed kind of related, where the abstraction is even more kind of obvious. And so by using abstraction, these artists can kind of help focus the viewer on specific aspects of the form, and in this case, maybe just have them focus less on the figure herself and more just on kind of these shapes and these contours. I think something that's clearly related to abstraction and maybe not quite opposite, but a different way of kind of manipulating form is to exaggerate things. And there's a variety of different ways that artists exaggerate form. So on the left, we have an example of exaggerating a pose. So this is a sculpture that sits outside of AT&T Park in San Francisco. And here the pose of this picture is being exaggerated to kind of really emphasize the tension in this moment right before the pitch is thrown. Actually, I looked up this particular picture because I was curious after I saw this the sculpture, and this is actually not exaggerated that much. This picture has a very particular kind of pitching motion, but it's exaggerated to some extent. And of course, exaggeration happens in the actual form of these objects, forms of objects as well. So in the Burghers of Calais, the hands and the feet of these figures are kind of much larger than they would really be. And some have speculated this is kind of to emphasize the kind of feeling of despair of these figures. So if we've talked about form thus far, but there's also a lot of abstraction and exaggeration that goes into texture as well. So in these cases, the textures of these various, in this case, I guess it's all animals, they've been exaggerated to kind of emphasize some of the features of these objects. And there may be different reasons for exaggerating and abstracting away texture, but this is clearly a technique that artists use as well. Conveying motion is another kind of interesting challenge, especially if you're considering a static sculpture. So before I talked about creating these automata, but these are static sculptures, and you really do get a sense for the motion of this ballerina as well as the motion of this wave. And again, I think pose is a good way pose is one tool that artists can use to kind of convey and emphasize certain aspects of emotion. But on the example on the right, this is kind of I think an interesting use of texture to kind of try to convey that emotion as well. I talked a little bit earlier about materials. I don't have a lot of expertise in this domain, but I'm sure that designers who create things like furniture, for instance, think a lot about materials when they're trying to convey. Is this like a luxury chair, or is this a kind of something that's supposed to look more modern, or something that has a different kind of feel to it? So I think materials and the choice of materials is clearly a really important tool as well. This is another example that I found kind of interesting. I have some interest in just kind of miniatures. I feel like they're really interesting. If you ever kind of see like a miniature of like a car or some object, it's kind of interesting what details are left and what details are abstracted away. So this could be related again to what I talked about earlier with respect to abstraction. But I think in the case of creating miniatures, it's kind of a very particular type of abstraction. I think it's related to icons in that, let's say you have a set of headphones. That's kind of the thing you want to represent. If you create a 2D icon of those headphones, you're kind of trying to keep certain details and abstract away others to still make sure that icon remains recognizable and has some features of the original object, but it's also legible. So clearly you can't include all the details. And I think similarly, we can think of creating miniature sculptures or miniature 3D objects as kind of this iconization problem in some sense, but in 3D. So I think it's kind of an interesting thing to think about. There's also, I think, a lot to be gained by thinking about what intermediate representations artists use to create these different types of artwork. So in the case of bas-relief wood carvings, as you can see on the top, oftentimes artists will start with some kind of initial illustration and then simplify it and annotate it in various ways in order to come up with the final design that they then carve into the wood. And so thinking about how artists use these intermediate representations, what they do with them, how that kind of illustrates or elucidates part of their design thinking, I think is an interesting potential opportunity. Similarly, we can think about concept sketches in product design as another type of intermediate representation. So that's a bunch of kind of specific examples of possible techniques from art and design that we could, maybe use to help inform design tools. Let me just talk really briefly about one last project, which is kind of some ongoing work that it's just kind of one example of how we can hopefully leverage some of this information to build a specific design tool. So in this work, we're really focused on the problem of helping people design what is sometimes called wire-wrapped jewelry. So a very different domain than mechanisms. And this is the type of jewelry that we're talking about. I guess it's kind of obvious. It's wire that's wrapped in some particular way to create some kind of design. And so, one observation about these wire-wrapped jewelry pieces is that they often start as sketches, which is probably not surprising to you all. And so the sketch, you can think of that as either the input or in some sense already kind of an intermediate representation. Probably like an unannotated sketch, that's probably more like the input to this design process. But at some point, you have to take that sketch and then figure out how the different parts of the sketch correspond to the different segments of wire that you're going to attach together to create the final piece of jewelry. And so the problem, or the kind of the approach that we've been taking, is to say, okay, well, let's say you have an input drawing. So this is provided maybe by either you find this drawing somewhere, or you create the drawing yourself, and now you want to turn it into this piece of jewelry. How can we help? How can we help make that process happen? And as I said before, kind of the main design challenges here, the main challenges in going from the thing on the left to the thing on the right, are one, to figure out which parts of that drawing kind of should correspond to different wire segments, and then actually kind of doing this wrapping. Like, how do you actually create the final thing from the design? And the pipeline that we've come up with is kind of a two-stage thing. So first, from the input drawing, we just want to help people come up with this wire design, which more or less is just a segmentation into the different wire components. And then, kind of interestingly, to help them go from that design to the final piece of jewelry, we are investigating some techniques to kind of help them print these kind of what we're calling custom jigs, that will then allow them to kind of wrap that piece of jewelry in a reasonable way. So I'm not going to say very much at all about the approach here. We kind of formulate this problem of taking an input drawing and turning it into this kind of segmented wire design as a graph-based energy minimization problem. So we're just trying to figure out, okay, should we take this segment and turn it into one piece of a wire, and then this other segment should be another piece of wire? And there's a bunch of kind of design goals that we try to kind of incorporate into that optimization. Like, you obviously don't want one segment to stop somewhere in the middle, and then another segment to kind of meet it at a sharp angle, because that's going to be hard to attach and it's not going to look very good, and that kind of thing. So there's a bunch of different kind of I guess energy terms that go into that represent these different design goals that we're going to use inside of this optimization. Let me just show you some results. So these are some preliminary results where we take as input the drawing that's shown in black in the middle, and these were kind of inspired by real pieces of jewelry that we saw online. So in some sense, we're kind of cheating because we know there is a solution already. But on the other hand, we can kind of evaluate our solution against what was actually created. So in simple cases like the butterfly, we can actually represent the whole thing with a single piece of wire. So that's kind of like the ideal case. But in other situations, we have to kind of use multiple pieces of wire to realize the design. So that's kind of the case that you see here in the bottom. Here are some other examples that are a little bit more complicated. We're trying to run these on much more complicated input illustrations as well. You could probably argue that for the examples that you see here, the segmentations we're coming up with are somewhat obvious. That may, yes, go ahead.
Sorry, just a clarification.
Yeah.
This was motivated by taking wires and sort of wrapping around. When you're 3D printing it, are you is it actually wire at all, or is it just sort of?
No, yeah. So I'll get to that on the next slide. We're actually not printing these outputs at all. So part of the challenge here with wire-wrapped jewelry is that it's really hard to print these really thin filaments and kind of get them to wrap or anything. So we're still actually there's still a human kind of involved in the fabrication process. Maybe it is actually the next slide. Yeah. Okay. So there's still a human involved in the fabrication process. So let's say I have an illustration and I get this design. This design just involves a single piece of wire, and now I have to I want to create this piece of jewelry. So what you could do right now without any assistance from our tools, just to take that piece of wire, cut it to the right length, and then use a pair of pliers and your hands and whatnot to try to create the final result. I'm not going to show, I don't have a picture of what that would look like, but it would look bad, trust me. Like, it's really hard to get the wire to basically bend smoothly in the right spots. And so what we've been trying to think of are ways in which we can help people, take their designs once they get to this stage and create the final piece of jewelry without, being able to actually 3D print that piece of jewelry directly, right? And so the approach that we're taking is to actually create these kind of custom jigs. So given a design, which our system now knows about, can we 3D print a jig that you can then use to kind of help wrap wire around in order to create the final results? These are just a couple of kind of initial experiments that we've been doing along these lines. The one on the top is kind of like the obvious solution, right? Like, I have this 2D design, more or less, and I want to have the wire basically represent that design. Why don't I just kind of extrude the whole thing, make a groove where I can put the wire into, and then wrap things around it? What's interesting here, actually, is that we found that wasn't actually that easy to use. So it produced a reasonable result. So the thing on the top is what was produced with that kind of extruded version. But it was really hard to kind of keep that wire tucked inside of that groove, and you didn't have any way of kind of applying tension to the wire as you went around. So that was kind of interesting, we thought. So we've been experimenting with different, actually, other types of jigs that we can derive from a given design in order to kind of make that wrapping process easier. And so that's kind of the part of the work that's not really done yet, where we've been exploring different ways in which we could kind of create these jigs. But obviously, we want to be able to do that automatically or computationally given the design. So that's kind of where that project is at. So that's kind of an interesting, I think, I'm excited about that project. I think, actually, in general, jewelry is an interesting domain for thinking about design tools. But I think there's some other opportunities as well. So let me just leave you with a few other specific opportunities that I think are kind of fun things to work on. And, for some of you, I might be interested. I mean, I'm happy to talk about possible projects to do, because I'm always looking for cool people to work with. So here are a bunch of different kind of automated or semi-automated design tools that I can imagine kind of coming out of some of the observations that I made earlier. So with respect to kind of doing abstraction of sculptures, one possible design tool could involve taking like a 3D scan of your bust, of a person's head and shoulders, and then kind of modifying that scan and abstracting it in kind of a sculptural way, basically. So knowing about the planes of the head, knowing about certain types of exaggerations that sculptors use, can we kind of basically improve these 3D scans of people's heads and to turn them into nicer looking sculptures? And so this is actually a project that some of my colleagues at Adobe have been doing in collaboration with other folks. And so it's kind of an ongoing project. But I thought it was so cool. Like, actually, learning about that project was one of the reasons I started thinking about this whole space of like, how can we kind of learn from 3D artists and build some better design tools. So I think that's one great example. As I mentioned before, I've been interested in this problem of like turning 3D objects into like what I would call 3D icons, so like smaller versions of them where you're trying to figure out which details to retain and which details to kind of abstract away in order to create a final result that's both recognizable as well as legible at that size. So I think that could be an interesting problem to work on. I talked a little bit about how artists who work in relief kind of go from input drawings to the kind of final design. So I think there, similarly with the wire wrap jewelry project, maybe we can think about ways of helping them kind of move along that workflow, kind of going from these input illustrations to the final design. That could involve things like simplifying different parts of the illustration and figuring out, where to put certain types of undercuts or certain types of features, physical features. So I think that's potentially an interesting project to do as well. And finally, going back to that sculpture of the picture outside of AT&T Park, I think it could be kind of cool to start from motion capture data, where you have the motion, you know the motion that you're trying to represent, and then turn that into a static form of it, a sculpture that represents that motion in some kind of interesting way. So that technique could involve trying to exaggerate certain aspects of the pose or certain aspects of the proportions in order to kind of really emphasize different aspects of the motion. in kind of a different space, and not talking so much about design tools, but probably related to design tools, we could think about trying to synthesize or understand what stylistic elements of different objects are kind of similar or different, and maybe use those for synthesis or maybe making automated design suggestions. So I don't have a lot to say about this because it's kind of high level and vague in my mind, but I think this could be an interesting opportunity to look at. And then finally, even more vague and hand wavy, one of the nice kind of outcomes of the work on non-photorealistic rendering in graphics has been to gain some insights actually by looking at what lines artists draw or what lines people draw about how we perceive things. And that's kind of a cool result. I mean, I've not been involved in that work, but that's, I think, a really nice a nice outcome for that branch of research. So maybe by analyzing and understanding more what techniques 3D artists use, maybe we can gain some insights on how we as humans perceive things like form and texture. Possibly. That could be a cool thing to investigate. And that's it for my talk. So I think I've left some time for questions. I'd be happy to answer them now. Thanks.
What's the scale of that?
Oh, that's it's I think it's actually human size. I don't think it's huge. I'm not sure though.
It's not yours.
It's not mine. No.
It's nice.
It's yeah. I thought it was really nice. Actually, unfortunately, I forgot to note in the notes where this actually came from, so I can't even tell you who the artist is. But I can try to find it if you're interested.
I actually want the opposite. I want to wear something that looks like it's made. So I have chiseled physique, literally. So I'll jump into the question.
Sure.
So you started out by talking about works like prototypes, right?
Yeah.
So sort of, essentially they're functional prototypes. They're trying to ask the question of, I have this vision that I think this would be feasible. Could I actually build a thing that mechanically does this?
Yeah.
And I wonder if we shifted our view towards something that's not quite a functional or works like prototype, but something like almost like a might work like prototype, something that's more like, I want to have this thing, flap wings when I do this. Like I think it would get less focused on the details of how do I create armature that sort of exactly reproduces this thing, and more about sort of fluidly conceptualizing new points of view or new ways of going about this, which especially in the early stages of design feels like what you really want to be enabling, not the I don't know how to do this. It's just eventually some mechanical engineer can take this, and as long as it's feasible, they can figure out how to do it. I just want to know if it would be even feasible to collapse this thing down.
No, that's a nice observation, and I think for sure, there's kind of different parts of this kind of different parts of the conceptualization of a possible design. There's kind of like, this kind of broader idea that, as you're saying, like, oh, what if I make like a chair that can fold up into a box? Like, that's kind of like at a high level. I'm like, oh, like this is kind of an interesting idea to explore. Is it even feasible? I'm not sure. The part of the design process that we were more focusing on is, once you're a little bit further down that road, you're like, okay, I think this is going to work. Let me create a physical thing that lets me kind of evaluate how it's working and whether this feels right. So I think there is a nice opportunity to say, okay, can we have a design system that takes even higher level functional kind of potential functional goals, like this may not even be feasible, as you're saying, and then tries to kind of explore some different possibilities, give me some suggestions, and say, oh, I think you can do this kind of this way, or maybe this other way, or this particular idea is not even feasible at all. I think could be really useful, as you're saying, kind of at that earlier stage in the design cycle. So yeah, I mean, we were kind of more focused on a somewhat kind of smaller, more specific problem, which is simply it's more one of execution. Like I have this design in mind, and I know how it's supposed to work. I know it's going to work. I just want to actually realize it in a way that allows me to kind of test it physically. And so that's kind of the part that we were focused on. But yeah, I think that's what you talked about is a really nice and sounds like a challenging problem to try to address.
We're rummaging around in an interesting space here, because I feel like motion is the thing that's hard, both in traditional graphical interfaces and physical interfaces. The thing that's hardest to conceptualize in your mind's eye. Yeah. Last week we had a speaker in my class who's a motion graphics designer for Google and had done a bunch of work in the film industry before he went to Google. And it's very like they have to do all this stuff in After Effects, so like in order to get anything that like eventually becomes like, you know, flipping hamburger icons, say, in Android. Yeah. And it seems like making that process of like, what would it be like if the thing swung over? What would that like? I feel like there's such opportunity there. Yeah, I mean, almost like as an input modality, like if you can also make use of motion, like as like, hey, or here's like, how do we? Yeah, I think that would. Yeah, that's really interesting. Yeah. Gilbert.
Anyone else have a question?
I think you had your hand up.
So, the thing that makes me think that this makes me think about is how much what's the process which designers or people making things are going through versus I want this thing in a sort of functional specification, which seems to run through a lot of the work, as opposed to, you know, another way to think about I want to create this mechanical object is I'm going to get a bunch of stuff and throw it on the a desk, and now I'm going to start, you know, sticking it together with Play-Doh, and it seems like there's a more not just exploratory process, but that it's tactile, that it's a different sense of, it seems like that's a different way of thinking. Yeah. And so I wonder how much these tools not just provide for people to like, oh, here's a way to do this easier, but really it's recasting the whole creation process as something more symbolic or more declarative.
Yeah, I mean, that's a good point. I'm not exactly sure how to respond to it because I don't think I know the answer. I think that you're right that I can certainly imagine aspects of the process or examples of this process happening in a much more exploratory way. And in fact, one thing I'm really interested in looking at that's related to works like prototypes or prototyping in general is how to go from these so-called like junk prototypes that designers often create early on, like using like foam core and like wire and whatever they have at their disposal, to just try to get a sense for this initial, you know, like how could this thing work, to the things that I was kind of showing, and you know, I think maybe one potential answer is to say, okay, well, can we more directly integrate the results of that kind of junk prototyping? Because you know, one of the disadvantages one of the advantages of using physical things is that they're just there. They're tactile, as you're saying. You can explore them. You don't, you know, often, you know, designers use things that are immediately at their disposal. So it's incredibly immediate. But then, you know, if you want to explore design variation on this one thing that you've constructed out of cardboard and paper, that's hard because you have to build another one or destroy this one. And so like digital tools have these nice advantages of like undo and like save and copy and paste and like all these kinds of things. So if there's some way we can kind of help bridge that gap, that could be really cool, right? Because then you might get some of the benefits of both of these worlds. But you know, I'm not really answering your question. I think that in part one of the observations with the worksite prototyping, that project, was that I think there are some cases where this kind of declarative notion of functionality, especially at the level of this thing covers this other thing, this thing is supposed to fit inside, you know, can be a useful alternative to just really low-level geometric editing or just directly editing the parameters without that information. And so that's kind of the initial kind of place where we started from, saying we can surely make this process better. Maybe we can make the process fundamentally better by considering some of the things that you've talked about, which we didn't have a chance to do, basically.
The use of junk prototypes is an interesting metaphor. I mean, like Walter Seki also has been thinking about like, you know, what if the designer could leave their junk prototype made out of Play-Doh or whatever on the desk overnight and come back and it's actually much nicer and maybe it has some armature or something. It's like it's like Jello. I leave it and it sort of sets a bit more.
Yeah, I mean maybe that piece of junk that you leave has gone off and built some other things on its own as well. Like that could be really cool as well.